Jadi juga nggak ke.
Morning, Mister. Yeah, hello. Yes, Kenneth. Good morning. Sir. Yeah, morning. Good. So everybody is already here? $14, $13. So okay, I think we just need to start. Let's pray first. Dear Lord Jesus, thank you so much for today. Thank you so much for everything. Thank you, Lord, that you have allowed us, Lord, to study and to wake up this morning. May you enable us, Lord, and bless this session of mathematics lesson. We pray all these things in the name of our Jesus Christ. Amen. Okay, so thank you guys for all the submission of the assignments. Okay, I will start marking them today. Okay, to finish and to catch up the marking the assignments. Now we're going to learn a new topic. Basically, not new topic, a new subtopic, which is the continuation of the differentiation. Now, I want to let you know that for the SA2, the topic is all about differentiation. Okay, finding tangent, finding normals, finding the what do you call it, and like today, the first principle of differentiation, the limit x approaching 0, fx plus h minus fx over h. That's the first one. The second one is finding tangent line using the concept of differentiation, finding normals. And the last one is which is actually what we are discussing for today. So only those four subtopics in one big topic, which is differentiation. Okay, that's our SA2. Again and again, that's our SA2. So it's basically the whole chapter 19, but with addition with the finding the normal line. Does everybody understand about this? Questions, guys? Go ahead. Questions? Do you have questions?
I don't have any questions, Mr.
Okay. Now we start the the actual lesson, the topic. What happened there? Wait guys, there's technical difficulty. Okay, today we are going to learn about the stationary points. So stationary points is actually also the application of differentiation. So the definition of stationary point is that stationary point is, guys, please don't do this. Don't do this. Don't make me so mad. Okay, don't do this. A stationary point of a function is a point where the first derivative of x is equal to 0. It could be a local maximum, local minimum, or stationary inflection. Okay, now starting from the simple concept, maxima and minima. Maximum, minimum. Okay, consider this graph from -5, the domain, -5 to 6. This is the domain here. -5 until 6 here. Okay, so this is what we call is local maximum. Why is it local maximum? It's because it's actually the maximum locally in this function. It's going curvy like that. Okay, here. So the point B is the local maximum, while the point C is what we call local minimum, because it's going down. Here it's going up and then goes down. This is what we call go up, down. This is what we call local maximum. Down, up, down, up. This is what we call local minimum. Okay, so A is the global minimum as it has the minimum value of 9 on the entire domain. B is local maximum here. Okay, A is the global minimum. Basically, what it's trying to say is that out of all these equation, this is what we call the global minimum. Basically, out of all the position or the point, this is the one that actually totally the minimum, the lowest point. This is what we call global minimum. This is what we call local minimum. So both of them are minimum, but the ones that actually say the minimum of all, we call it global minimum, is in A. Here we have is local maximum, and this is what we call D as global maximum. Okay, here A is global minimum, because out of all the minimum points, this is like the lowest. Okay, the lowest. And then the B is local maximum, and this is the
Mister,
D is the global maximum.
Sir, Jepta can't join, Mister. His laptop is lagging.
Yeah, thank you. I already read his message.
Oh,
Thank you.
okay.
Okay, okay. Do you get it, guys? The idea of global minimum, global maximum, local minimum. Global maximum. Why is it global maximum? Because compared to these two maximums, This is higher. But this is still maximum, but it's local only, not the global. And this one, or we can also call universal maximum, but rarely being used, but we can call it as just global maximum. Here, out of these minimums, this one is less than this. That's why this one we call it as the A is global minimum and C is local minimum. Okay. So, but there's like exception. For example, for many functions, a local maximum or minimum is also can be the global maximum or minimum. For example, y is equal to x squared, the point OO is both okay. In this case, if you see at the 0, 0 is simultaneously is the global minimum or and also at the same time is local minimum. Global minimum and also local minimum. Okay, do you have questions about this? Okay, not all functions have both global and local maximum or minimum separately. Sometimes one point also describing it as the local minimum at the same time also the global minimum. Like in this function, y is equal to x squared, point 0, 0 is the local minimum and also the global minimum of this function. Okay, okay, let's continue. So, for example, the other points, yeah, do you have questions? Kenapa ada local, sir? Yeah, it depends on the nature of the function. Okay. So after we know about the minimum or maximum, we also need to know that there is the what we call as the stationary points of inflection. Okay, wait for a moment. Okay. So stationary point of inflection is different from local and global maximum or minimum. So basically, that's actually the point of inflection. The what they call it. It's like this is the point of inflection. So the change.
To read his way up.
Yeah, there.
Daryl.
Oh yeah. Okay, nggak apa-apa. Understand. Okay, thank you. Now, here I said to you, besides the idea of local, maximum, minimum, and global minimum and maximum, there's another one about stationary point of inflection that you should know. Okay, so the idea is that about like the x-axis is like this. In this case, is the function of fx is equal to x cubed. Okay, the x-axis is a tangent to the curve which actually crosses over the curve at O. Okay, this is the idea. When there is the idea of tangent which is horizontal, is neither a local maximum nor a local minimum. It is called a stationary inflection as the curve changes its curvature. So the idea of stationary inflection is basically when the curve changes its curvature. Here, the changes of curvature from here becoming this. This is what we call the stationary inflection. Makasih, Pak. Okay, 0, 0. The stationary inflection, the point of stationary inflection is at 0, 0. Okay. Now, here, this is the actual example. You will see the idea of local maximum, local minimum, and stationary inflection in this example. Now we need to start from the idea, why is it called plus? Why is it called minus? Why is it called plus? Why is it called plus? It's called plus because it's going upward. Okay. In this region, why it is called plus? Because it's going up. Here, why is it called minus? Because it's going down. Okay. And then here you go up again, we call it plus. Here we go up again, we call it plus. Local maximum happen when there is a transition from plus and minus. Up, down. Between them, in the middle of them, that's what we call local maximum. Down, up, minus to plus, the transition, that's what we call local minimum. And stationary inflection is basically the transition between the same thing, plus to plus. Okay? When the curve bends or stationary inflection, but in terms of the trend, the trajectory, they are just still the same, plus plus or minus minus. That's what we call stationary inflection. Now, this is actually using the concept of also of gradient. I actually draw for you here. This is actually the idea of sign diagrams here. Here, as you see, it's going up. I draw red triangle. Going down, I draw the blue triangle. Here, go up again, I draw red triangle. And then if you see this go up again, I draw red triangle. So local maximum happens when there is the transition plus and minus. Okay, red to blue. And local minimum happens when there is the down to up or blue triangle to red triangle. And stationary inflection happens when there is the red triangle, up to up, or can be also blue, blue, down, down, down again. Okay, minus, minus can be. Okay, I don't want to go too far. Do you have questions, guys? I need to stop for a moment. Do you have questions?
What is this about, Mr.?
Stationary points. Local
Mister?
maximum, local
Okay.
minimum, stationary inflection, which is
Mister?
also the application of differentiation. I'll show you what the differentiation took place later. But do you guys get the idea? The geometrical perspective first.
Mr. This one has a relation to differentiation.
Yeah, later.
Buset, okay.
Okay?
Mister?
Yes, excellent.
Mister, for the stationary inflammation, the where tangent is horizontal, no
Yeah.
maximum minimum. Is it always on the x-axis?
No, not always. It depends on the function.
Okay.
Okay, it could be it's not at x is equal to 0. You will see later. Okay. Okay, let me continue. Okay, so as I said to you, the stationary point where here, the first derivative, it has to be equal to 0. So the relationship is this. What the relationship between differentiation and local maximum, local minimum, and stationary point of inflection is you only can get the local maximum or local minimum when you have your first derivative or the first differentiation equal to 0. That's the relationship about all these things that we are talking about with differentiation. Here, this is the requirement. The first derivative is equal to 0. Okay. Now, let's see a real example. So, consider a function fx is equal to x cubed minus 3x squared minus 9x plus 5. A, find the y-intercept. B, find and classify all stationary points. So the question B is asking, is there any local maximum minimum or stationary point of inflection? Hence, and or therefore, sketch the curve y is equal to fx. Okay, first one. The y-intercept only happens when x is equal to 0. So when all 0, what remains is only 5. So f0, 5. So the y-intercept is equal to 5. Easy. Find and classify all stationary points. Now, the only thing that you actually can solve question B is you first need to differentiate the original equation. X cubed, when you differentiate, become 3x squared. Minus 3x squared, when you differentiate, become minus 6x. And minus 9x, when you differentiate, what remains is only the number. So you have 3x squared minus 6x minus 9. And then all of this has common terms, which is 3. Put 3 outside the bracket. 3x squared, 3 times minus 2x becomes minus 6x. So you put minus 2x here. And 3 times what? That becomes minus 9. Minus 3. After that, you have, because this is you need to get to know that the f action x is equal to 0, then you need to factorize this. When this one is equal to 0, what happens is that you have two factors. X is equal to 3 and x is equal to minus 1. X minus 3 is equal to 0. Then x1 is equal to 3. X plus 1 is equal to 0. Then x2 is equal to minus 1. Then you have minus 1 and 3. The problem is that you don't know whether the minus 1 is the local maximum or local minimum. That's why you have to sketch the curve, the original curve. But you know the transition of local maximum or local minimum happens either in minus 1 or 3. Okay. Okay, I think I need to. Here. As I said to you, minus 1 and 3. See, it's totally clear that minus 1 is local maximum or local minimum, guys. Here.
Maximum.
Okay, good. Thank you. And this one is local minimum. Okay. So it's really the main thing to know this is finding the f action x is equal to 0. This is the point or the key to know your turning points or your local maximum or minimum or even later station points of inflection. Okay. So you get minus 1 and 3. In order to find the y coordinate, you just plug in here to the original equation. Don't put it into the first derivative equation. No. To find the y coordinate, you need to plug into the original equation. In this case is x cubed minus 3x squared minus 9x plus 5. Put it when x is equal to minus 1 and put it also when x is equal to 3. And you get 10 and minus 22. So we can say that minus 1 and 10 is our local maximum coordinate. And 3, minus 22 is our local minimum coordinate. Okay. Now this is the second example. Find and classify all stationary points of fx is equal to x squared plus 1 over x. Now, for me, first we need to simplify the equation in order for it to be differentiated easier. Because in terms of this, it's hard for you to differentiate. So what I do is that I separate them. Okay, so x squared plus 1 over x, I put it one by one. X squared over x plus 1 over x. And then it's basically x plus 1 over x. Okay, 1 over x is basically x power of minus 1. And then fx here, x power of 1 plus x power of x. This is what we need. Which is the same function with this, but I need this so that it's easier for me to differentiate it. Okay, now second, differentiate the function. So we have 1 here, 1 times x power of 1 minus 1. And then here, power of minus 1 here. Minus 1 become the coefficient x minus 1 minus 1. It's always minus 1 for the power because that's the rule of differentiation. And then here what we have is f function x is equal to 1 times x power of 0 because 1 minus 1 is equal to 0. n minus x power of minus. So what we have is the final result of the differentiation is 1 minus x power of s. Okay, or to make it positive, this basically equal to 1 minus 1 over x squared. Go to the Desmos and graph the original function. So this is the original function. Now we can see that it's minus 1 and 1. But is it true from our differentiation? Is it true from our algebraic problem solving? This is what we call graphical problem solving. Now, as I said to you, it has to be the first derivative is equal to 0. So what we should do is that here, 1 minus 1 over x squared is equal to 0. Now, in order to do this, I need to make sure that the denominator is the same. So I convert 1 become x squared over x squared. So what I have is that it's basically x squared minus 1 over x squared. And then the key is you have to factorize this. So what I have is x plus 1 and x minus 1, which is the factorization result of x squared minus 1. So therefore, you can see here, there are 3 critical points that we need to pay attention to. Remember, everything this equal to 0. So we start from here, x plus 1 is equal to 0. So we have x1 is equal to minus 1. And x minus 1 is equal to 0, then x2 is equal to 1. X squared is equal to 0, then x is equal to 0. This is actually undefined point. Why? Because it's in the denominator. We cannot make x is equal to 0 because it will be undefined function. Okay. Now we go here. Fifth, state the nature of the point. Okay. Now we go to here. We already find it's 1 and minus 1. And at x is equal to 0 is undefined here. This is what we call last time is as a reciprocal function. Okay. You still remember that. So at x is equal to 0 is undefined function. So here we can say this is the global local maximum, and this is global minimum. While also at the same time, it's a fact that here not only it is a local minimum, it's also local global minimum. And here minus 1 minus 2 is not only local maximum but also global maximum. Now, do you have questions?
None from me.
sir. Everything's fine.
Fine, yeah. Okay. Now, this is, I want to check first. Is everybody is here or not? So I will do absences. So
Jepta.
everybody, please show your beautiful and handsome face.
Here, sir.
Saya baru bangun, Mister.
Okay. Wilbur. Thank
Udah ya,
you.
Mister. Bye-bye.
What do you mean bye-bye? Wait. Richter, are you there?
Iya.
Felicia, are you
Mister
there?
mau nonton lagi baper. Bye, Mister.
Nggak ada. Masa belajar ya belajar, nonton. Jeffrey, are you there? Felicia, are you there? Axel, are you there?
You know.
Okay. I'm okay if you're
Oke,
eating.
Mister. Oke.
Okay, good.
Oke, Mister.
Hello, Wilbert, Jeffrey. Wilbert,
Kan
are you
homo-
there?
Homo banget, ya, Ken.
Yes, Mister.
Wilbert, are you there? So who are missing?
What?
Romeo is here. Romeo is here. No, yeah.
Sir, can I turn off my video now, Mister?
Romeo is not here. I think Ethan is not here. Ethan. Romeo is here or not? No, yeah, Romeo.
Turn off my camera, ya, ba? Mr. Bye.
Okay, that's okay. You may close the. Okay, now this is practice time for you guys. So I want you guys to apply the knowledge that you actually already get. And I will grade it as active participation. Here,
Knowledge.
do this. For each of the following function, find and classify any stationary points. Sketch the function showing all important features.
Enggak main, basah bajunya.
Makasih ya. Ya.
Hmm? Hmm? No.
Do we really have to sketch, Mr.?
No. So I will show you what you should do. Okay. Don't answer it yet. Don't answer it yet. So guys, here write down the question. Now after that, I'll give you instruction what you need to write down privately to me in the chat room. Don't start answering now. Later. Remember guys, this is graded. Aduh, don't write it down yet. Later. Okay, you have about 2 more minutes, guys.
Mister, I still don't get what is inflection, mister.
What?
I still don't get what an inflection is. And in fact, yeah, inflection, yeah.
Inflection is basically when the trending of the graph stays the same. For example, like this, up to up. So it doesn't have anything to say up, down, or down, up. It's just up, or down, down. That's actually when the stationary inflection takes place.
Oh. Okay. Thank you, mister. I get it now. Thank you. Do we need to sketch, mister?
I said to you, no, you don't need.
Is there any formula on finding the local minimum or the max?
See the chat room that I gave you.
Okay,
I already write down to everyone. That's actually the kind of format that you should type it privately to me. Okay, 1 more minute. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Now type your answers, guys, in the chat room privately to me.
Wait, mister, can you give me a little bit more time?
What?
Can you give me a little bit more time? I'm about to.
Okay, let's put this way. For those of you who need more time, after this meeting, rejoin again. I give you extra 5 minutes.
Thank you, mister. Hey.